The name of the tutorial talk, it's Impact of Lower Atmosphere Wave Sources on the Thermosphere and Ionosphere. And this talk will be given by Dr. Tim Fuller-Rowell. And Tim Fuller-Rowell, he received his PhD in physics in 1981 from the University College London. And he's currently at CERES and the Space Weather Prediction Center.
Thanks, Sharon. Yeah, and thank you for the steering committee for the invitation to present this tutorial. So the title is The Impact of Lower Atmosphere Waves on the Thermosphere and Ionosphere, very similar to what Jeff's title on Monday. And okay, I'll just lean forward. So of course, that was an excellent tutorial. This is, I don't really see my talk as being a conventional CEDAR tutorial, which is what we do know about the system, and I think Jeff's was probably more of a tutorial than mine will be. Grand Challenge tutorial, it's supposed to be what we don't know, so it's a bit of an oxymoron, a Grand Challenge tutorial. So hopefully I'll have a slightly different flavour to my talk than what you heard on Monday. My background is on thermosphere-ionosphere modelling, and we tried to understand the response to solar and geomagnetic activity. But it was sort of more recently that I've got more involved and interested in the impact from the lower atmosphere when we started to develop a whole atmosphere model about 5 or 6 years ago. So I'm a bit of a student in this myself, so which is why it's also not so much of a tutorial. So what I want to try and more sort of pose some of the questions that we have rather than what we do know. And the things I want to try and address is what mixes the lower thermosphere, and what impact does that have in the mixing, and conventionally it's the turbulence, the gravity wave mixing. Then there's the global circulation, and there's also interest now in sort of tidal mixing or wave mixing. And there's actually a whole spectrum of waves that might be doing that. So first of all, I'll address that. And then there's also a day-to-day variability of tidal amplitude and phase. And we know surprisingly little about how that day-to-day there's very few measurements of the global tidal variability, just because it's hard to actually measure it, and what impact that has on the thermosphere, ionosphere, and what actually causes that tidal variability. And I'll probably save that to last and probably do this in the middle, which is the characteristics of the non-tidal gravity wave field that we're starting to look at with this sort of whole atmosphere model. So that's, and the context is sort of this I'm going to demonstrate a lot of these things in a whole atmosphere model that we developed about 5 or 6 years ago, and which I find fascinating and exciting. So coming from sort of modeling the thermosphere and ionosphere, this was our world. This is what our sort of thermosphere ionosphere look like if you just run a thermosphere ionosphere model. It's all nice and smooth. You get these, this is sort of temperature, you could say this is about 200 kilometers altitude, something like that. So it's sort of a global snapshot as a function of latitude and longitude, and so this would be local time. And so you see this sort of diurnal variation with a peak and a trough. So this would be like your, in tidal nomenclature, the DW1. So it's diurnal, because it varies. This whole thing would respond through had a 24-hour period. It's wave 1, it's one peak and one trough, and this whole pattern would follow the location of the sun. So it would migrate in longitude in that nomenclature. So it would be called, would be the in situ generated DW1. And then there's a latitude structure, and it's clearly the December solstice, it's hotter in the south, and so, but it's all nice and smooth. And then if you looked at the height integrated O to N, you get something like this, which again is very smooth, and it's difficult to compare. Sort of, there's not a good wind model, but you'd compare this with like the EMSIS empirical model, and you'd think, oh yeah, I'm doing quite well for the quiet global structure. So this is what sort of is this reality, or is this the reality at 200 kilometers altitude, the temperature? So that same figure, but just as an animation. It's actually sort of a 3-minute, this is just 1 day of data. And you can start to see, there's this sort of peak here and sort of a bit of a trough here. So that's that DW1. It's sort of moving westward with respect to longitude. So that's that migration westward. So that makes it one of the migrating tides. And so you can see that, bit of a secondary peak here. This is that midnight temperature maximum that was observed a long time ago that is now starting to come out of the model. This is clearly a simulation from this whole atmosphere model. And then, there's this whole spectrum of tides. The tides are things that have a periodicity that is some harmonics of 24 hours. So it would be one at 12, 8, 6, and you can keep going down. And if you look at a tidal analysis of this whole field, you'll see peaks all the way down to the 10th or 11th harmonic. But then there's other stuff that isn't anything to do with harmonics of the day. So you can see this sort of a nice wave feature here. There's clearly sort of gravity wave stuff that is on here. If you look at the scale here, this is about 300 Kelvin range here. So the diurnal in this main DW1 peak is maybe 150, 200 Kelvin. But then there's all this structure which is about the same magnitude as the magnitude of this diurnal variation. And the main diurnal variation. So there's a whole spectrum of waves in here other than just all of these harmonics. So we don't know. Is this reality? Don't know. We can't measure it. And if you go down, the source of all of this stuff is probably, obviously coming up from the lower atmosphere. This is what it might look like at about 110 kilometers altitude. This is where the DE3 would peak, that famous DE3. And again, if you look at the scale, this is sort of 200 Kelvin. Again, a lot of stuff. It's hard to sort of pick out is this reality? We don't know. We can't really measure it. But I want to try and convince you that a lot of the structure that we're getting out of this actually does agree with a lot of the observations. So the DE3, the amplitude of the DE3 in September at this altitude would be about 10 Kelvin. So on this scale, it's not surprising that it doesn't stand out. The DE3 would be it's wave 3 in the tidal nomenclature. So you should see 3 peaks somewhere. It's now, instead of moving westward like the migrating tides, it's now moving eastward. So you should be able to see sort of 3 peaks that are moving now eastward, and it would move eastward so that one of those peaks moves during a 24-hour period. It would just move 1 peak eastward, so the whole thing would just move a third of that pattern across. But I sort of keep looking at this. Can I see the DE3? Now, if you analyze it and look at to what all the tidal harmonics are, it does come out. But it's not obvious. It's because you've got all this other stuff going on all the time, probably. And again, if you go down another 50 or 60 kilometers down at 50 kilometers altitude, again, this is what the temperature, and this is the zonal wind. If I click on that one will start as well, I hope. Doesn't look like it's so variable. You can see that in this season you actually get a strong polar jet, and a lot of those big waves that we saw before up at 200 kilometers altitude, I think are probably due to sort of instabilities in this jet that are propagating up. So this is where that's just one of the many sources that it could be. And if you look at what that would look like, say at one location, just take a random location. I mean, these are actually 2 different locations, but it doesn't matter. And you look at the vertical profile of what the zonal wind might look like. Down at the lower altitudes, it's sort of slowly evolving because it's more planetary wave, and then all that stuff that propagates up reaches very large amplitudes in this sort of 100 to 150 kilometers altitude. You can see those huge excursions. What I want to try and convince you is that this isn't just numerical noise in the model. These are real gravity waves that are propagating up that have some source down here. That's one of the big questions. What are the sources? How do they change with season, with latitude? And this is what it may look like. This was a nice figure by Xian Liu from the WAM model that shows these. This is like the perturbation temperature. So by the time you get up to 200 kilometers altitude, you get these sort of plus or minus 100 Kelvin oscillations with periodicities of sort of 1 to 2 hours. So all this is sort of coming out of the model, even though it's, there's parts of the spectrum that we're not getting. And of course, all the different sources of waves, there's tropical convection, which is, and the longitude variation of that is creating a lot of that DE3 stuff, but there's the sources, actually thunderstorm sources, and of course Sharon's done a lot of work to try and sort of follow how the waves from particular thunderstorm complexes propagate up into the thermosphere. There's well, you can just sort of read down the list. I mean, they're all sort of obvious things that you can just Google and find out what are the types of sources of lower atmospheric waves, and there's loads of them. We don't have to sort of agonize over them. And then there's the sort of the types of waves, and you can, I mean, there's lots of ways to categorize these waves, but there's these migrating and non-migrating tides that I started to talk about. The migrating ones which are tied to the sun, and the non-migrating that can move eastward or whatever. Then there's the sort of stationary planetary waves, and there's whether they actually get up to, I mean, there's obvious stationary planetary wave that are caused by the offset of the geographic and geomagnetic poles. So you get a wave 1 straight away in the thermosphere ionosphere just because that offset, because of the geomagnetic pole not being in aligned with the geographic pole. But whether the planetary waves, of course you get loads of planetary waves in the lower atmosphere because you have all the influence of the land masses and things like that. There's all sorts of sources of stationary planetary waves. Then there's also all the normal modes of the atmosphere which have certain multi-day periodicities, and whether you generate those in situ in the thermosphere ionosphere is I don't really know. But the influence of all of these on the upper atmosphere, you can see. There's these gravity waves, the buoyancy waves, restoring forces, gravity. Then the inertial gravity waves, it's all gravity waves that are propagating, but their restoring force is the Coriolis force, geostrophic adjustment. And the meandering Rossby waves, where there's a latitude gradient in Coriolis. So there's all of these different classifications of how the waves are, all the wave sources. And then there's a whole class of acoustic waves, of course. So these waves can propagate or the waves that propagate vertically, and not all of them do, they grow in amplitude as it's increasingly rarefied due to energy conservation. And then there's some waves that get to the thermosphere, have very large amplitudes, and so they break and cause mixing, deposit their heat and momentum. And traditionally these breaking waves are the source of the turbulence and the main source of mixing in the thermosphere. And that's what we our sort of picture when we were modeling the thermosphere ionosphere over the last few decades is that was the mixing source. When we developed our thermosphere ionosphere model, so I just wanted to sort of give a bit of a historical perspective of how we sort of came to put in the sort of the mixing processes in thermosphere ionosphere models. And a lot of it was, these are, got a few of these profiles of, these are chemical trail releases. These are, got a few figures from Miguel Larsen. And there's a release of a chemical going up in altitude from the lower altitude, it's probably, 50 kilometers or something, and the top altitude maybe a couple of 100 kilometers. And typically, you've got all this sort of turbulent region up to a certain level, and then it appears to go from this turbulent regime to sort of a laminar flow. And that tended to be what you saw with all these chemical releases. So we have this sort of turbulent gravity wave, which is probably just sort of gravity wave breaking. I mean, that's the sort of what we think of them as being the source of this. But then there's also this natural transition. So we think of this sort of, well, this is sort of the turbulent mixing. It's the turbulence is actually an advective process. It's not a random process. It's chaotic, but it's deterministic, and it's an advective process. It's not actually we parameterize it as a diffusion process, but it's actually an advective process, and it's chaotic but deterministic. And then it seems to go to a sort of a laminar flow, and in this region we expect the molecular diffusion to take over, and so then you get the separation of the species. And this is sort of where it's all turbulent. This is nice animation from Mike Taylor and Dominique's all-sky camera of the air glow of OH at about 90 kilometers altitude. And you can see all of the waves that are creating all of this turbulence. And that's typically what you see. If you look at any profile, it's turbulent up to a certain level, and then it becomes laminar. And you can actually get a lot of wind shear and large wind velocities up here, but it never appears to be, it always appears to be sort of laminar, and the actual expansion of this trail always seems to follow what you'd expect from just molecular diffusion rather than sort of turbulence. So there's a lot of transport and wind shear and everything, but you tend to get all this turbulence down here and then laminar here. So we use this to model in our thermosphere ionosphere models to we adopt Eddy because we can't resolve all this gravity wave mixing because we haven't got the resolution. We use this concept of eddy diffusion. So although it's an advective process, we sort of parameterize it as a diffusion process, so that if you had some parameter up here, whether it's the velocity or it could be the temperature or the potential temperature or mixing ratio of a species, and if you have a sort of a vertical gradient, and there's a diffusion sort of between the layers of with a diffusion coefficient. So this is like your eddy diffusion coefficient. So the gradient across this layer. So this layer has an influence. So this is sort of, say if this was velocity, we'd want to try and accelerate this layer, and then the layer below is trying to retard it. And so this is trying to accelerate this, and this is trying to slow it down. And the relative balance of those is just second order. Differential in order to get whether the winds will increase or decrease at this level. So that's sort of like the basic how we put it in as a diffusion process. And the molecular diffusion will look exactly, well, would be viscosity for winds, would look just the same form. And so we're using that analogy with diffusion for this mixing process. And it can be different for the momentum or for the species diffusion, and there's these Schmidt and Prandtl numbers, which is supposed to be the ratio. It's just because of the complexity of the process of the gravity wave mixing. Okay, the actual eddy diffusion is not a physical process. The physical process is the advective mixing of the gravity wave breaking. So we're just trying to parameterize it in that way. So the impact of that eddy diffusion, say, on composition, we know it down at the lower altitudes below what we think of as the turbopause, where the turbopause is where there's our concept of an eddy diffusion is about the same magnitude as the molecular diffusion, and which is just the random process of the individual molecules, which is a real physical process. And when those two when our parameterized eddy diffusion is about the same magnitude as our molecular diffusion, that's around 110 kilometers. So you get all these mixing cells down in the lower altitude, and so it mixes the atmosphere very well, and so you get roughly the same mean mass all the way up to about 110. And then in the molecular diffusion, all these the individual species start to separate out with their own scale height, whereas here they separate out with the total pressure scale height. And if you have more mixing, this turbopause will go up a bit, and the altitude where they would where it would start to go over to diffusive separation will be a bit higher, so you tend to have higher, this is sort of done in terms of mean mass, so you would have higher mean mass, you'd be mixing up more of the heavier species, so you would have a higher mean mass, and if the gravity wave activity was a bit less, then the turbopause would go down, and it would start to separate out at a lower altitude, so your mean mass would be lower, you would have less of the heavier species and more of the oxygen. So if you vary, say, through season, the magnitude of the gravity wave parameter, if you increase the KZ, the turbopause would rise, you had more mixing, you'd have more of the N2 and the O2 at the higher altitudes, you'd have a smaller O to N2 ratio, the scale height would be smaller, so the atmosphere would be more the increase in KZZ, have I got this around the wrong way? Oh, that's embarrassing. The increase in the eddy diffusion would sort of put more of the N2 and O2, so this would be bigger, the scale height would be smaller, and the atmosphere would be more compressed. So I have got that the right way around. And if you decrease the amount of mixing, you'd have more oxygen, and the scale height would be bigger, and so the atmosphere would be more extended. And the change in the O to N2 ratio is also going to feed into the loss rate for the ionosphere as well. So this is our sort of concept. And this sort of mixing process is true whether you have if you're changing the Eddy diffusion coefficient, this parameterization, or whether you have other forms of mixing. If you have wave mixing, some other sort of mixing, the same, you can apply those same principles of the impact of the mixing on the composition. Oh dear. In temperature, it's slightly different in temperature because you're mixing parcels of gas. If you move a parcel of gas to a lower pressure, it expands and cools. So the equilibrium temperature profile is the adiabatic lapse rate, which is just the temperature decreasing in altitude. Same reason why if you go up at the top of a mountain, it's colder. So if you increase the amount of mixing, it'll get colder, and if you decrease the amount of mixing, it'll start to go to the constant gradient. So it has the impact on the mixing on temperature has the same impact in terms of density and on the impact. So sorry, I didn't explain that very well. So can we use things like the eddy diffusion in order to try and this is one of the problems. We have a sort of a semi-annual variation in thermospheric density. If you compare neutral density at CHAMP satellite altitudes at around 300 kilometers altitude with what you would model just with a regular thermosphere ionosphere model, if you put in all of the solar EUV and UV sources and the geomagnetic activity, then there's a discrepancy between this. There's a semi-annual discrepancy, and what you can do is you can just vary this eddy diffusion coefficient as I was describing, and you can change both the if you have a seasonal variation in that eddy diffusion coefficient, you can change the amount of mixing, you can change the composition and the scale height, and you can change the temperature. And so there's some way that you can actually adjust that, but it's a bit artificial. And so that's one way of actually sort of matching that eddy missing semi-annual variation is by adjusting this parameterized eddy diffusion coefficient, but it's a bit artificial. And another way you can get mixing is through the large-scale global circulation, and this is to show that you don't actually have to have breaking gravity waves to actually create mixing. At solstice, you have a large-scale circulation from the summer to the winter pole, and that is transporting the molecular-rich gas from the lower altitudes, and that transports it up, and the oxygen then moves to the other hemisphere. And you can get a global circulation there's actually a sort of a net mixing, so that at equinox, the O to N2 ratio would be higher than typical. This is both MSIS and the observations from GUVI. So there's a net large-scale mixing by this whole global circulation, and this was one of the theories about what this semi-annual variation would come from. But it turns out that it's not sufficient. But what it does illustrate is that this large-scale circulation can mix the species and impact the O to N2 ratio and the density and the ionosphere without actually having to break the waves, without having to dissipate or break the waves. And another sort of mixing. Then we're starting to say, okay, well, rather than just looking at gravity waves and the large-scale circulation, you have a whole spectrum of tides now that we can force the model. And before we were just using a very simple tidal forcing at the lower boundary. So then we sort of introduced Moira's sort of a slightly more bigger spectrum of these waves, not a complete spectrum, of course, because as you saw in those early animations, there's a whole slew of the spectrum. But even just if you sort of increase from sort of one of these tidal modes at the lower boundary to 4 or 5 of them, you can see there's a mixing effect. This O to N2 ratio when you, this is just with the 2-2 mode, there's an offset between the observations, and you get closer to the observations, the GUVI O to N2 ratio. This is the function of the day of the year, and this is looking at it in latitude in December. So it gets a little bit closer if you had more mixing. So this is an indication that maybe there's sort of other sources of mixing. This idea has been around for a while, of course, but we're now starting to sort of examine it more closely because we have this whole spectrum of waves from things like these whole atmosphere models. And this is the whole, the spectrum of models, spectrum of waves that you could get. And so we want to look to see, what the impacts of that might be on the mixing. So about 5 or 6 years ago, we developed this whole atmosphere model. What we did was took the global forecast system, is the National Weather Service, the US National Weather Service weather model. That they have a model that goes up to 60 kilometers. So it's just this bottom bit here. So it has all of the stuff that you would expect for weather forecasting models. So we took that model and extended it up to 600 kilometers. So it's a 10-fold increase in altitude. It's got 150 layers, quarter scale height resolution. The weather model, of course, runs at about 25 kilometer resolution. We run it at about 180 kilometer resolution as a spectral model, just because it gets too expensive otherwise. So it has all of the sort of the lower atmospheric stuff, and then we have to sort of add all of the upper atmosphere and stratosphere and mesosphere physical processes. But instead of getting this type of patterns like the animation we showed, you start to get all of this stuff that's generated. So before it was sort of looked like MSIS, and now, when you first see it, you think, well, what's happening here? Must be a mistake in the model. But this is what's coming out of the model, and we think it's real. And you want to validate that. You have to make sure that it's all working well. And if you look at the DW1 down at 100 kilometers altitude, this is that same diurnal wave, westward propagating wave number 1. It's our normal sort of diurnal tide, but this is the one that's propagating up from sources. The source is down in the troposphere from water vapor absorption, and you can see this is the model simulation, and this is from Jeff Forbes' paper of what the CEDAR observation shows, sort of the average over a few years, and you can see it's pretty good. So we have to do a lot of validation, make sure that the model is working properly. And then if you look at that DW3 again, it looks pretty good, and it's seasonal. This is a version with function of month and latitude, and you can see the magnitude of that. The DW3 is about 10 Kelvin. 10 Kelvin. Yes, 10 Kelvin at 116 kilometers. And that was where you could see all of these waves and stuff that were sort of 50 and 100 Kelvin. So, but if you do the analysis, this is what comes out with WAM. So that's looking pretty good as well. So just I put a couple of slides here about that sort of tidal nomenclature, because it's frustrating when you get into it of trying to understand what they all mean, and some of it. So you have to, for the migrating tides, you have these DW1, the semidial westward propagating wave number 2. That's just the semidial tide in our sort of frame that we normally think of in the thermosphere. And then the terdial tide, so this is the 3 peaks, again, westward propagating, has to follow the sun, so it has to, every terdial, so every 8 hours, it has to move 1 peak to the left, westward, in order to follow that. So, physically you can see where they would come from, but the tidal nomenclature, it sort of doesn't really give you much information, but I think of it, these make sense physically, and planetary wave makes sense, because there's structure that is dependent on longitude, so you expect wave 1, wave 2, wave 3, that type of thing. And so in migrating tidal nomenclature, you have to say that for DW1, it's a wave 1, so there's 1 peak, 1 trough. It has to follow the sun, so it has to be westward moving, and it has to move through the whole cycle once every 24 hours, so it's D. So that sort of diurnal variation, that's how you represent it, and the same for the semidiurnal and the terdiurnal. That's how you represent those. For the non-migrating tides, then you have things like an eastward propagating wave number 3 with a diurnal period. why? Why does that happen? And we'll look at that a little bit in a minute as well. Another thing that the model seems to produce, another impact of waves impacting the upper atmosphere, this midnight temperature maximum. It's a peak that you get just around midnight. This is just half the globe, so this is just the night side, and you can get 50 or 100 Kelvin secondary peak at around midnight, and that appears to be. If you just look at all the tidal modes beyond from 3 and above, it seems like you get these sort of 3 peaks. So this would be like your TW3 mode. So you got wave 3, and it moves westward, and it's got an 8-hour period because you want this one peak to move 1 peak westward in 8 hours. And you can see that as you go up in altitude, this peak, because there's downward phase propagation, upward energy propagation, this peak this is around sort of on the night side, so it doesn't dissipate very much. So you end up with this peak here, and it's that sort of seems to be the energy is propagating up. This is that downward phase propagation, which indicates the energy is propagating upward. So it's this peak seems to be, survives and creates this MTM feature, whereas the other sort of peaks of the terdial tide seem to get damped. So if you were to do analysis of what that TW3 here was, the amplitude of the TW3 up here, it wouldn't be very big because you've lost the other 2 peaks. But it's almost like this sort of one of these peaks is propagating up like an individual sort of packet of, like a gravity wave or something like that is propagating up independent of the other ones. So you have to be careful about how you sort of apply all of that tidal analysis, but you have to sort of look at, well, what's the physics of different parts of those peaks. So it's nice that this is done a lot of comparison with some of John Merriweather's observations and Jonathan Mackler's observations of temperature at low latitudes, and this is pretty good. And you get the secondary MTM as well. Okay, so this DE3, and I always sort of struggle with again this. If you look at where if you look at all the lightning strikes from convective storms over a long period, I'm not sure how the period is, but you tend to get it over the land masses. I mean, that's where you get the thunderstorms, and so it looks like you've got sort of 3 peaks on this. I mean so when I thought, yeah, that makes sense. You can see why you might get a wave 3, but if you take that, if you assume that it's just 3 peaks. And you're illuminating it, I mean, you always tend to get the thunderstorms sort of late afternoon. So it gets modulated by the sun every 24 hours. So, okay, I can understand you might get sort of a diurnal. And then if, I got this from Jeff Forbes' Nicolay lecture 2 or 3 years ago. So if you have something that is modulated, so you've got this wave, say if it was wave 3, you've got this wave 3, and it's modulated by a diurnal variation, and in that tidal nomenclature, it's sort of like wave 1 of 24-hour period. And if you do that, cos A times cos B is half cos the A plus B and A minus B, just simple sort of, trig, whatever it's called. So here, this is diurnal, and then the minus makes it an eastward propagating wave, and it's wave 2. So that you would actually get DE2, not a DE3, if this was a wave 3. I think I've got that right. Jeff can correct me at the end of the lecture if I've got this wrong. But that was sort of my interpretation of that. So clearly it isn't, that's where it's good, you can see where you might get a DE2 coming, but in fact it's, this is a 90-degree separation here, and it's about 90 degree here as well. So you've actually really got, this is actually 4 peaks. It's just that the other peak isn't very big. But if you did a analysis of this, you actually get another peak here. So if you did have if it was a wave 4, illuminated over 24, you do the same thing, and then you get the DE3 coming out. So whether you get a DE2 or DE3, maybe, you know, at times when the monsoon's on and things like that, then, you know, you get a different sort of balance of these. Maybe you get the, you know, changes between the DE2 and the DE3, and I'll show an example of that as well in a minute. So, you know, you just get to the point where, okay, I understand why you get a DE3, great. And then they tell you, so, well, you actually get 4 peaks. So this happens because if you're observing if you've got 3 peaks, and you observe it with a sun-synchronous satellite, so that in 24 hours, the Earth is rotating under this satellite during the 24-hour period. If this was just a wave 3 that wasn't moving eastward, then you would just have these 3 peaks, and as the Earth rotates, the satellite would sample these, so you just get nice 3 peaks. But because it's moving eastward in 24 hours, it just moves 1 peak to the east, so that the satellite will see those 3 peaks, but then during that 24-hour period, those 3 peaks will have moved 1 peak to the east. So it'll actually see 4 peaks rather than 3 peaks. So that's why you end up getting 4 peaks. So now we're back to, you know, I mean, that's the frustration of all of these, both the observation systems, what you see, and all this tidal nomenclature. But it sort of does make sense, I think. Okay, so we've got this model. We think it's working well. We've got this whole spectrum of tides, and I have to hurry up. And so if we look at all these spectrum of tides, get back to this semi-annual variation. Why don't we try and sort of vary the eddy diffusion coefficient? Why don't let's just put in all of these tides, and they dissipate, and we just put them in as every hour we average the monthly temperature, zonal, meridional wind, and the height of the pressure level down below about 100 kilometers, just force the model. And we seem to be able to capture this missing semi-annual variation if we just put in all of those tidal fields. We sort of filtered out all of the gravity wave field, but it's all the tidal fields, all the harmonics that we would have kept in that. But it seems like this work that Marangel is doing, that if you use those WAM fields in CTIP, it seems like you can capture that. So it seems like there is a lot of that wave mixing that is coming from the dissipation of all of those tides, and in fact there's several other people that have been working on this type of activity at NCAR as well, and so you get this semi-annual variation in mean mass because there's different amount of mixing and different months, and you also see this difference in this is just the difference between with and without the WAM fields imposed, and you can see where it's actually coming from. Sorry, I have to rush this a bit. So there's a whole range of types of this is just getting into the mixing part, which is 10 minutes behind. So you have this turbulence, you have the molecular diffusion, which is creating the mixing. You can have wave-induced chemical transport that I haven't really talked about very much, and so that if you move the wave up and down, and there's actually some sort of chemical thing where there's recombination, where the wave is at one part of the cycle. So you can have wave-induced chemical transport that I haven't included very much, but I haven't talked about. There's when all these tides and gravity waves dissipate, they create a little circulation cell, and there's a really nice paper by Yamazaki and Richmond recently on that. And there's also sort of wave mixing, even though, you know, from the waves and superposition of the wave, non-interaction, and Jeff talked about this a little bit as well. And I must admit, I don't sort of totally understand where that comes from. But the idea that you can have the global circulation mixing without breaking waves, I think you can have a superposition of all of this spectrum of waves that create mixing even without the dissipation. But that's a bit sort of vague at the moment. And then there's circulation driven by zonal wind. So there's lots of mixing processes. It's not just this turbulence and the large-scale circulation, which is what I started with. There's all this other stuff. So I did want to, I'm going to jump to the impact of this sort of non-tidal wave spectrum. So if you did tidal analysis, you get peaks at all of the harmonics of the 24-hour period, but there's all this other stuff in the middle, and you can see it all here. You know, if you do a tidal analysis, you know, half of the energy is coming from all this non-tidal wave spectrum. I don't know if it's half, but a good bit of it. All of this stuff. So again, I want to sort of try and convince you that the stuff that is coming out of the model is real, and we can actually sort of use the model to try and understand it. And that going back to those chemical trails, that this laminar part of the trail, there's Miguel Larsen and his students they can look at the vertical profile of the neutral wind field from that. They can just track it, using cameras and triangulate. And you get these huge wind shears. You can get wind shears of 50 meter per second per kilometer in altitude. Huge wind shears. The old thermosphere models sort of never got that, and even when we put the geomagnetic forcing in, you still didn't get it. And so you've got this sort of huge wind velocities of sort of 100, 150, even up to 200 meter per second. This is sort of going from 80 to about 140 kilometers altitude, 160, sorry. And then they don't keep growing, assuming that these are sort of gravity waves that are propagating up, which is what we think they are. Then they dissipate by molecular viscosity. They don't break, as far as we can tell, but they dissipate. So molecular diffusion, ion drag, things like that are dissipating these waves. They don't necessarily have to break. Some of them may do, but we don't know. But you get these huge wind shears, and those wind shears, we think, just as I showed you, as these gravity waves are propagating up and they grow in amplitude. And so you get these huge excursions up to 200 meter per second, just like those observations. These are the observations. And if you just look at one day of, one location of these profiles, you start to see some of this. These are the same scale, zonal wind, same altitude, 80 to 140 kilometers. And you can see the same sort of magnitudes and structure, and this is there's a lot more profiles here. But you get that sort of growth of these gravity waves and this is what they would look like when you get up. And I showed this figure before. So I believe that all of this stuff they're not numerical things. They're growth of these gravity waves just because it looks like the wind fields that you observe. And not only that, if you compare with some of Jing Zhao's LiDAR observations, that sort of structure of the vertical propagation in temperature, and you can see it in winds as well, you get that sort of structure in the LiDAR. This is in the FE LiDAR. This is LiDAR concentrations. So you see that structure. If you look at the vertical winds, it's actually at the South Pole from Gonzalo Hernandez, there's all this fluctuations. You get the same sort of stuff coming out. So you can get the horizontal winds, the vertical winds, and this vertical structure. It all looks very consistent with a lot of the observations. You can also put all of these wind fields into an ionospheric model. And so this is what Tzu Wei, I forgot to put a name on that. Tzu Wei did the simulations where you put all these WAM wind and temperature fields, you feed them into the ionosphere-thermosphere model, and you can see all these sort of fluctuations of the planetary density. And these are observations from Juth at Arecibo. You get the very similar sort of structure. These are about plus or minus 15%, and you get the same sort of magnitudes. And if you look at a Dynason, these are the Doppler velocity, vertical velocity, plus or minus sort of 5 meter per second. You get in the same sort of structure coming out. So, and there's a lot more of part of the spectrum here. We haven't got the full part of the spectrum here because limited resolution. But all of these waves that are propagating out, this is just the temperature profile, and you can see what they look like. So it seems like it's getting into the ionosphere as well, just as you'd expect. And if you look at, of course, now I talked about the mixing of the tidal waves and the eddy diffusion, but you've also haven't even looked at really the mixing yet of all of this whole other part of the spectrum of waves. So this is the vertical wind, this is the meridional wind, every 3 minutes through a day, and if you sort of plot it so that you get the aspect ratio, this is sort of 2,000 kilometers, about 20 degrees in latitude, and over 100 kilometers out. So if you scale the vertical wind, but just by the aspect ratio, so you can see the relative motion. So you scale these by 20 in terms of the length of the vector. You can see that this is the resolution of the model. You can see all of these sort of swirls and things that are actually impacting this is the oxygen mixing ratio. So there's a whole thing of mixing that you can get from these gravity waves as well, probably. And so one other thing, I've got to. Another grand challenge that we have in the ionosphere is the ionospheric irregularities that you get at low latitudes. If you raise the ionosphere up near the equator, it becomes gravitationally unstable, and so the ionosphere wants to come down again, but it's restricted because it can't get across the magnetic field, and so you have to introduce some sort of undulation on the so that the Rayleigh-Taylor instability allows the plasma sort of to fall down, and so you have these low density sort of streaks coming up through the plasma, and then the high density plasma is trying to get down. So it's sort of trying to exchange the plasma, the high plasma density for the low plasma density. But you have to sort of try and that sort of varies from day to day. You have sort of seasons of irregularities, but just some days they go and some days they don't, and that's another grand challenge is trying and predict that. What we did was put in all our wave fields from WAM into John Retter's irregularity model, and again, the actual seed is probably, the individual seed at the small scale that he models. It's probably numerical, but there's definitely something about the wave fields, these large-scale wave fields that are coming out of WAM that cause the irregularities to go on some days and not on others, and in addition to the electric fields that were causing the plasma to. So this is another whole area that I can't spend much time on, of course. And in terms of the source of these waves, this is just one example of where we were trying to trace back where some of these waves were coming from. And in this case, it appeared to be down to about 50 kilometers, which is where you got that strong polar jet. And if you look at the downward phase propagation, which is upward energy propagation, it looks like the source region is sort of down here. This is where you can scale the fields by density, by altitude, so that you can get them to stand out, and you can actually see these waves that are propagating. Seem to be coming from about 50 kilometers, where there tends to be a lot of wave activity. So you can use this type of model. This is just one example of the whole, one of the possible sources. So just in the last 5 minutes or so, I just wanted to go back to the impact of the tides again. We showed that if you put in a whole spectrum of tides, you get. Oh, good, thank you. You have this whole spectrum of tides, all those harmonics of 24 hours, and we know that they dissipate and create mixing. But those tides also generate electrodynamic. They get into the lower thermosphere in the dynamo region, and a lot of the sort of like the semi-diurnal tide will drive a lot of the electrodynamic, a lot of the electric fields that you get in the thermosphere, ionosphere. So they're two competing processes, and that Yamazaki and Richmond paper sort of showed that they're sort of actually competing mechanisms, so that the tidal mixing is changing the O to N2 ratio, which can give you a decrease in the plasma density, but then the increase in the tides can change the strength of the electric fields that can actually increase the strength of these equatorial ionization anomalies. And so they're sort of competing processes on very different time scales. And surprisingly, we don't really have very good observations of if you have a global tidal fields that are changing on a few day period. We don't really know how they're changing, because SABRE, a single satellite takes it's at least 30 days to sample all local times to get the magnitude of these tides. So you don't really know what how the amplitude and phase of these tides are actually changing. So that's we need more observations for that. And we also actually still don't know really what what's actually driving that tidal variability. It could be the source region, the ozone, or the H2O, and of course there's a huge number of changes that are going on in the source region. There's atmospheric resonances and the Forbes and Zhang paper, and I'll go through some of this in a little bit more detail, and I think I've got a few more minutes. And then the actual sort of the propagation through these different background fields. If the whole global circulation in the stratosphere and the mesosphere is changing, even though the source region might be the same, the way that those waves propagate up can be quite different because of the change in the zonal winds. So this is just sort of taking a period. This is a paper, Sue's paper, where we took she took the WAM fields over several days, and you can look at the changes in the amplitude of. I mentioned the DE3 and the DE3 and the DE2. I showed you that maybe the relative balance of the convective storms in those different sectors. And I mean, this is September, so you got probably got the Indian monsoon sort of coming and going during this period, and this is the amplitude, how the amplitude of the DE3 and the DE2 changed over this September period, and you can see that some days it's strong and some days it's weak, and then some days the DE2 is strong and sometimes the DE strong and weak, and then because that tidal field is driving the electrodynamics, you get different. And if you have a DE3, remember you got 4 peaks at a given local time. You get 4 peaks, and so sometimes you get 4 peaks and sometimes you get 3 peaks, depending on whether the DE2 or the DE3 is the strongest tidal mode. And even though they tend to be small, because it's sort of globally large-scale coherent, then you see the signatures in the electrodynamics more than you do in a lot of the small-scale stuff. And so that sort of global structure can be driven, even though the amplitude of these might not be huge compared with all the other stuff, because it's globally sort of coherent, then you see the electrodynamic influence of that much more strongly. This is just looking at the variation in the SW2, and that, again, in that same period, the amplitude is changing and will modulate the amplitude of the NMF2 and the vertical plasma drift. So it's just the impact, just showing some of the potential impacts of the amplitudes of the tides, the phase and the amplitudes of the tides. And the other example I wanted to show was sometimes you can get really huge changes, 50% changes in the plasma density. This is just quiet, and this is stuff from that's by Larissa, and you get this really large increase in the total electron content that you can measure from these ground-based GPS, and then at other times it would be less. And we think that's due to the changes again in those electric fields, the tides, then changes in the tides for some reason, producing very different electric fields and producing the strength of the equatorial ionization anomaly. This, of course, was in January 2009 when there was this really strong record-breaking sudden stratospheric warming, which is changes in the circulation in the stratosphere, which changes the whole global circulation in the middle atmosphere. So it changes the way that the tides propagate up through this region. This happened to be what they call a wave 2. This is that same tidal nomenclature. So wave 2 is, when it started, it just got a very, we'll go back to the beginning again in a minute. You got a very symmetric vortex, so there wouldn't be any particular wave 1 or wave 2. If you have this sort of structure, this is the vorticity in about 30 kilometers out. So this would just be sort of like wave 0, if you could call it that. If that thing just tilted off the pole, then if you go around in longitude, you see one peak and one trough. So you call that wave 1. Because it splits into 2, going round in longitude, you'd see 2 peaks. So you say it's wave 2. So that splitting of the vortex gives you a large wave 2. If you look at the prevailing, instead of being eastward, the winds reverse to westward. And then when those waves propagate up through that region, they're very different, and we think it produces all of that. And this is the observations of the electric fields from Koki Chow's observations at Hickamaka. And you can see this is just the day side vertical plasma drift. So normally it's sort of upward during the day, and you get this change in the phase, so the upward drift occurs. This is as a function during this stratwarm period. This is the stratwarm signature, and so it tends to introduce this sort of vertical upward drift early in the morning and downward in the afternoon. And just taking all the tidal fields from WAM, and you can simulate this. Wang has simulated this period because it's a weather model. you can use all the data and use all the NSET, all the National Weather Service data assimilation system, so you can actually follow this strat warm, and you actually can reproduce all the wind field changes, these SW2 and TW3, and you can seem to reproduce the electrodynamics that you see that then produces all those plasma density changes. So, you know, exactly what's happening in the model that causes that could be the changes in the source region, all the changes in the ozone that create this SW2, this semidial, westward, wave number 2, and because you can see that there's a lot of horizontal mixing as well. I mean, that's something we haven't really talked about. As well as this sort of vertical mixing process, you get a lot of horizontal mixing, and because of all of the advective and the circulation changes, and you can see sort of peeling away of the ozone down at 35 kilometers altitude. And so when this whole circulation changes, it peels away the ozone, so you can changes in the ozone. This is a comparison just at one location. It shows good agreement. So, you know, and so that's one possible source of the changes in the tidal amplitudes, and the sources change. And this is what Larissa has been sort of trying to advocate. Could be due to that. We haven't got a lunar tide in WAM, but Jeff Forbes argues that it could be a change in the resonance to the response to the lunar tide. The lunar tide has this sort of characteristic as well. It's just that it's about 3 times or 4 times more intense during this period. But there is a sort of a natural semidial resonance in the atmosphere, precarious resonance. And if the changes in all the wind field that we talked about change the atmospheric, the actual period of the resonance closer to the lunar period, which is this 12.42 hours, and if you shift the atmospheric resonance closer to that, maybe you get a much bigger, 5 minutes? Okay. Maybe you get a much bigger response to that lunar tide. And so this is what Jeff is advocating, and you get this factor of 3 or 4 increase in the magnitude of the. If you look at the SABRE data, you get an increase in this M2 lunar quasi semidial tide, and maybe that's what's driving it. We don't know. Or it could be just the solar driven tide. Even if you didn't change the source region, if you change the propagation of the solar-driven tide, this is the stratospheric winds. This is the change in the phase of the SW2, the solar-driven SW2, and it seems like, there's good correlation between the changes in the wind circulation and the reversal of the zonal winds from eastward to westward and the changes in the phase. You can imagine that if you've got this sort of tidal variation, if the atmosphere is stationary and it would just propagate up. With the downward phase propagation, it would just move to earlier local times. But if the whole atmosphere is, instead of moving eastward, is now moving westward, you're carrying that tide a little bit eastward, so it sort of like tilts it over. It changes the vertical wavelength of in that context. So maybe it's maybe that's just it's trying to follow, this phase is trying to follow it's just being carried by the background winds. So as well as an amplitude change and a phase change, they all feed in. Maybe that's the source, we don't know. So that's my talk. So I hope I've convinced you that all of the stuff that's coming out, some of the modeling is and this is not all the whole spectrum either. I mean, that cuts off at about 25 minutes, and if you look at some of the other observations, it looks like that. And so is this the reality or not? Who knows? And then this was a figure that Hanley Liu gave me, where they're actually running Wacom, the one that goes up to 150 kilometers, now at 25 grid, horizontal grid. So there's lots of fascinating stuff, I think, over the next decade to look at, and so in conclusion, now appears that there are multiple sources of mixing in the lower thermosphere. We've got the day-to-day variability of the tides, and then there's also this sort of non-tidal stuff. And I think these are all the things that we can look at in some of the workshops that will follow this. Thank you.
Thank you, Tim, for a very good talk. We must have questions. Questions? Well, I have a question. In terms of seeing the daily variability of the tides, you obviously need to have some sort of daily measurements, and maybe should you have a few different locations? I mean, what would be the best thing from your perspective in order to get the tidal variability? Because that's...
Yeah, I mean, it's a good question, and well, I mean, Jeff showed the idea of the dynamic mission that was proposed in the decadal survey, where you, or even in his talk, where if you had 3 polar orbiting satellites, then you could actually resolve enough of the wave number field and build up a spectrum of the migrating tides, on a daily basis rather than on a multi-day basis. So, or you'd have to have a lot of ground-based observations in order to do the same. But ideally, if you had a constellation of 3 satellites that were observing the wind field, then you could build up that tidal, the day-to-day variability of the tides, I think. But
would they need to go
well, you probably know better than I do, actually.
Upper to lower latitudes? Would they need to shift in latitude, or would they be
yes,
at the...
Yes, you need that as polar orbiting,
okay.
and then covering enough of the longitude sectors to build up, separating out the migrating and non-migrating components.
Okay. Huh. Yes, Alan.
Yeah.
I see your plot showing the discrepancy in the semi-annual variations.
Yes.
I don't remember its density or temperature, but I see that in the smaller time scale variations, they actually match quite well, like on the several days.
Those peaks.
Yeah,
yes,
those peaks.
They're the excursions. They're the excursions due to geomagnetic activity. So the solar and geomagnetic modulation, I think, is sort of captured quite well. It was this sort of semi-annual that wasn't captured very well, which is a similar magnitude, it turns out, than a lot of those peaks, which were from moderately sized geomagnetic activity disturbances. So that's just when the high latitude dual heating increased due to the changes in the solar wind and put energy in and cause the atmosphere to expand and then recover by NO cooling. So yeah, we can get a lot of that temporal variation, but the background was annoying because we couldn't really get that semi-annual.